All right, so this video is to help you to remember how to graph polar graphs. All right, it's going to be a little long. If it's too long-winded, feel free, to fast forward through the parts that you do remember. All right, but I just wanted to make sure that I do a thorough job. Okay, number one, you can check your work by having your graphing calculator in polar mode and radian mode. That's number one, all right? And you could do, like, your theta min could be 0. Your theta max could be 2 pi, right? Your theta step, you could just do, if you really want a nice smooth-looking graph, say pi over 24. Okay, your x min, it depends on the question. How large your radius is going to be, but pretty much you could try like -2, +2 for the x max. Okay, y min, -1, y max, okay, 1. And you can play with this part. All right, so let's start. First kind of polar graph we have are circles. Okay, what does a circle equation look like? You're just going to have r equals, okay, say cosine theta, or you might have r equals 2 sine theta, but it's going to either be cosine theta or sine theta times a number, okay? I'll also do a negative example. I'll do r equals -2, all right, cosine theta. So I'll do these 3 examples. So think about it, all right? Think about what's going on. So when you're dealing with r equals cosine theta, okay, you're talking about your diameter is 1. So your diameter goes in front of here. So the diameter is equal to 1. Here your diameter is going to equal 2. Okay, but this one is going to be a reflection because of this -2. Here the diameter is equal to 2. Now cosine, whenever you have something with the cosine in it, it's going to be symmetric over the x-axis. Because think about this formula, right? Think about it. You have x equals r cos theta. So this is going to have symmetry over x-axis. The sine, think about y equals r sine theta, that equation. So this is going to be symmetric over the y-axis. Okay? So here you're just going to have a little circle. Okay, your diameter is 1. So this point here is 1, 0. For the sine one, okay, your diameter is going to be 2. So think about the radius here. Okay, radius is 1/2. Keep that in mind. It's going to be symmetric over the y-axis, and you're going to have a diameter of 2. So let me go up to 2 here. 1, 2. All right. So this point is 0, 2. Then for this -2 cosine theta, it's going to flip onto the other side. Okay. I think I said reflection over y-axis. Oh, yeah. Maybe I said x. I don't remember. But anyway, it flips over to the other side. So I have 1, 2 is my diameter, but it goes over here on the other side. So this is -2, 0. Okay, those are circles. All right, so let's move on to the next thing. Now, these circles, by the way, they graph one full cycle from 0 to pi. This is extremely important. All right, you're going to need to memorize over, all right, what interval you graph one full cycle. So this is one full cycle for your circle. Otherwise, you're going to go over your circle more than one time, because we're going to be getting areas and we're going to need bounds of integration. So that's where we're going to be going with that. Okay, so those are circles. Now, you could always do it by hand. Okay, you could always make a chart, just to let you know. So let's say you were doing r equals -3 sine theta. And you wanted to just make a little chart. Your chart would go r theta. Okay, you would start with your theta. Now, I'm only going to be going from 0 to pi. So I would pick out values that work well for sine. So sine works out well with 0. It works out well when you have pi over 6, because the sine of pi over 6 is a half. Pi over 2 works out well. 5 pi over 6. And of course, pi. So your radius is going to be -3 times 0, so it's starting at 0. So if you wanted to just graph it by hand, you'd start at 0, 0. Then at pi over 6, we're going to have -3 times 1/2. -3 times 0.5, which is -1.5. So you go to pi over 6. You know pi over 6 is over here. All right, but then we're going to graph a radius of -1.5. So since it's negative, you have to march out in this direction, 1, right, and then a half. So pi over 2, so this is headed around in this direction. Okay, I'm just drawing an arrow in the direction. Pi over 2, the sign is 1. So this is going to, the radius is going to be -3. So if I went up to pi over 2, right, here's pi over 2, but I'm going to go backwards, 3. 1, 2, 3. Okay, if you finish that up, it's going to end up going around like this. Okay, so you could always resort to doing that, but you only need to go from 0 to pi. So 5 pi over 6, the sign was also a half. All right, but then you had to go backwards again. So this was -1.5, but 5 pi over 6 is here. So then you go backwards, which gives you a point over here. And then you end up at pi. Sine is again 0, so you get back to 0. So you're traveling around the circle in this direction. All right, so now we're going to look at limacons, okay? A cardioid is a limason too. So we're going to have, I'll do 3 examples with you. We're going to have r equals, say, 2 plus 2 cosine theta. I'll do that example. Okay, then I'm going to do r equals 1 plus 2 sine theta. And then I'm going to do r equals 2 plus cosine theta. Now, we call this number A and this number B. So A equals B here. When that's the case, you're going to have a cardioid, which is going to be a heart-shaped graph. Here, your A value is less than your B value. So in that case, you're going to get a cardioid with an inner loop, okay, which is called a limason. The C gets this little hook on the bottom, limason. And then in the last one, okay, so these are all cardioid graphs, but these last two turn into limacon. So here you have your A value is 2. So A is greater than B because B is 1. So this is going to be a dimpled limacon. So it's going to have a little dimple. It's not going to make an inner loop. So this limacon is going to look like a cardioid. It's going to be a cardioid with an inner loop. Okay, this dimpled limacon is not going to have a loop. It's just going to go in like a little dimple on someone's cheek. Okay, so when you're graphing these, all right, you have this 2 and 2, okay, are going to give you the distance, okay, that you are from the origin. So you're going to end up at your greatest point, you're going to be 4 away, your greatest distance away. So that's 2 plus 2. Now, as far as graphing it, if you make a little chart, r theta, these are going to graph out from 0 to 2 pi. So from 0 to pi, you'll get half of the graph, all right? Now, since this is cosine, the cosine values that work out well, all right, are 0, pi over 3 instead of pi over 6, because that's going to be a half, pi over 2, 2 pi over 3, pi, all right, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 2 pi. Okay, so I'm going to have 2 plus 2 cosine theta, which is going to be 4. So my graph starts here at this point, right here. Okay, then when I have pi over 3, I'm going to have 2 plus 2 times a half. So that's going to be 3. Okay, but pi over 3 is all the way up here, kids. So you'd have to go out a distance of 3. Pi over 2, you get 0 for cosine, so this is just 2. So you're just going to go up 2. So you can see it's heading this way. Then when you get to 2 pi over 3, you have to think about the cosine value. Okay, in the second quadrant, cosine, all right, cosine, you're talking about the x value. X is negative, so that's going to be -1. So, I mean negative a half, sorry. So you're going to have 2 minus 1, which is just 1. So you're at 2 pi over 3. So here's your 2 pi over 3, but you're only going out 1. Then at pi, you're going to get -1 for the cosine. So you're going to have 2 minus 2. So that's going to be 0. So it's going to go in right here. Okay, and you could figure out the rest of the chart. I'm not going to do the entire thing by hand. You can also use symmetry here. So that's a cardioid. Let's look at the limacon. We're going to do 1 plus 2 sine theta. So number 1, this is going to be symmetric over the y-axis. So we're going to have r theta. We're going to go to 2 pi. But because I'm dealing with sine here, I'm going to use pi over 6's instead. Pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, 11 pi over 6. All right, so I have sine of 0 is 0, so I'm just going to get 1. So I'm going to start at 1, which is going to be over here, right? So that's my starting point. Then when I have pi over 6, sine of pi over 6 is a half, so I have 1 plus 2 times a half. Well, 2 times a half is 1, so I just get 2. But pi over 6 is down here. So you'd have to go out a distance of 2, so it would be about here. Pi over 2, sine of pi over 2 is 1, So I get 1 plus 2 is 3. So this is going to go up to 3. Okay, so you can see it's going this way. And then 5 pi over 6, sine is the height. In the second quadrant, sine is positive. So you're going to get the same answer as pi over 6 here, but 5 pi over 6 is this way. So that's going to be 2 again. So I'm just making it look symmetrical with the other side. And then when we go to pi, sine of pi is 0, so we're just going to get 1. So this goes to 1. And then 7 pi over 6. So 7 pi over 6 is in the third quadrant. That's negative a half. So you're going to have 1 plus 2 times negative a half, which is going to end up being 0. So at 7 pi over 6, which is, you know, here, you're not going out at all. You're landing here. Okay? So that is 7 pi over 6. But then what ends up happening is when you go to 3 pi over 2, you're talking about the sine being negative 1, right? So you're going to have 1 plus 2 times negative 1, which is negative 1. So what ends up happening is you end up going up here, okay? But you're going to make a loop. So this is 0, and then 2 pi is 1. All right, so you could figure that out. But what's ending up happening here, right, when we went all the way we started at 0, and when we went around, you can look at the symmetry, you can see that by the time we got to 7 pi over 6, we went to 0, right? But if you wanted to think about going halfway, you know, you could always start at another spot. Like, you could start, instead of 11 pi over 6, you could think of starting at negative pi over 6 and starting with this point here and then traveling in this direction. You know, so it depends on where you're starting your problem. Okay, so the bounds of integration are going to change depending on how we look at symmetry and how we choose to do the problem when we're doing our polar area. Okay, but you're not going to be able to do polar area if you don't have a clue of how these things look. So now we're going to look at this dimpled limacon. Okay, you can try to do it by hand, okay, if you want. This is going to go out 3, 2 plus 1. Okay, it's going to go around just like the first problem did on this page. But then what's going to end up happening is, instead of going all the way into the origin, you're just going to have a dimple here, kind of like a lima bean. All right, and then it's going to go back around. So you could certainly try to do that by hand, but you don't need to hear me do that one by hand as well. All right, let's talk about rose curves. Rose curves are tricky. They usually ask us to find the area of one petal. All right, we have to be careful here. So the first thing is, okay, when you're looking at the coefficient, so for rose curves, okay, I'm going to show you the difference between having a rose curve with an odd coefficient of theta Okay, now when you have an odd coefficient of theta, you're going to graph the rose curve from 0 to pi. All right, otherwise the petals would end up graphing, all right, on top of one another. If you went from 0 to 2 pi, like, it would literally graph on top of itself. So you'd have like one rose on top of another rose. All right, so we're going to start with this. So let's say you had r equals 3 cosine 3 theta. Now this 3 is the length of your petals, okay? This other 3, when you're talking about an odd coefficient, okay, this means that you're going to have 3 petals. If we're talking about even coefficient of theta, you're going to be graphing this from 0 to 2 pi. Now, let's say you had r equals 3 times sine 2 theta. So in this case, okay, the 3 is again the length of the petal. What's tricky here is this 2 theta. You have to double the 2 to get 4 petals. So remember, if it's even, you're going to double it. Okay, so as far as graphing these, okay, we can use symmetry. So remember, cosine is symmetric over the x-axis. So your first petal, okay, will be here. And then you're going to have 2 other petals, and we can do this by hand as well. Usually they're going to ask you for the area of this one petal. So you have to know where it's starting and where it's ending. Or what a lot of people do is they just do half of the petal and then double it. Okay, these are not easy to graph by hand by any means. Think about this 3 theta, right? So focus on this 3 theta. Think about nice values of cosine. So if I want to start off with 3 theta being 0, that's a nice value, then I'm going to want 3 theta to be pi over 3, because cosine of pi over 3 is a half, right? I'm going to want 3 theta to be pi over 2, because at pi over 2, cosine is 0. So I'm going to start with these. So for the first one, theta is just 0. For the second one, theta is actually pi over 9, because I divide both sides by 3. Okay, for the last one, theta, okay, is actually pi over 6. So what this means for us, if I take 0 and substitute it in, I'm going to start here. All right, because cosine of 0 is 1. 3 times 1 is 3. Now, when I take pi over 9, which is pretty flat, and I substitute it in, I'm going to get a half, because I'm going to have cosine of 3 times pi over 9, which is pi over 3. Well, cosine of pi over 3 is a half. 3 times a half is 1.5, so you're going out 1.5 at pi over 9. So that's going in this direction, you see? Then when you get to pi over 6, you're getting to 0. So if I went to pi over 6, right, this is pi over 6, I'm going to be at 0. So when you go to get your bounds of integration and you're dealing with this problem like this, okay, I have my start, I have my finish. This is half of my area of one petal. So you're going to have to think like that. All right, now let's look at the bottom one. So first off, this is going to have symmetry over the y-axis, right? Okay, then I have to think about getting one petal. So, and the length of each petal is going to be 3. All right, I'm not the the best at drawing these. By no means am I an artist. I have an appreciation for art, but by no means, all right, have I ever invested my efforts into that. So you have 3 times sine 2 theta. So here you need to think about, focus on one of the petals, right? So sine, you know, is going to start at 0, right? So if I take this 2 theta, I'm going to set it equal to 0. That's going to be a nice value of sine. The next nice value of sine is pi over 6, because that's a half. And then the next really great value is pi over 2. So if I solve these, I get theta equals 0. Theta equals pi over 12. And then I have theta equals, okay, pi over 4. So when I substitute in 0, sine of 0 is 0. So that means I start here. Pi over 12, which is going to be really low. When I substitute in pi over 12, I'm going to get sine of pi over 6, which is a half. 3 times a half is 1.5. So that just means at pi over 12, we're going out 1.5. Okay, so that's, say, this point here. So we're headed in this direction. Now when theta is pi over 4, you know, is just symmetrical right here. When I substitute that in, I'm going to end up with sine of pi over 2, which is 1. So this is where you're going to see the petal length of 1. Okay, so kids, from here to here, okay, which is from 0 to pi over 4, I'm getting half my petal. Okay, so keep that in mind. Half my petal, if I wanted a full petal, I would double the half, right? But you're going to make this as easy as possible when we get the area. So you're going to have to think about half a petal, how you're going to get the half a petal, how you're going to get your bounds of integration, and then how we can use symmetry to get the rest of this. Okay? Okay, the last one I'm going to show you is the lemniscate. Okay, I did realize that I wrote petals like as if I was talking about a pedal on a wheel, on a bike, whatever. I don't really care. It's not going to affect the math. Okay? But anyway. So we're looking at this. This is a lemniscate, all right, which is a figure 8. All right. I haven't seen them make kids graph this by hand. But what ends up happening, if you were to get the square root, like let's say you were solving for r, right? Negative values would be imaginary. So that's why you just end up with a figure 8. So it looks something like this. You don't end up with these petals because those are imaginary. All right, so just keep that in mind. I'm not really too worried about it. Okay? But if you wanted to get, say, one part of this and then use symmetry, so let's say you wanted to get this part here, you would have to think to yourself, all right, when or what are our bounds of integration going to be, right? Okay, so I'm going to have this 2 theta. I'm going to set it equal to 0 because I'm going to start at 0. So that's just theta equal to 0. Then I'm going to think about when you would be headed toward, say, 0, right? So think about what cosine is good again. So I'm going to have 2 theta equal, okay, to pi over 3. So that means theta would be pi over 6. And then I'm going to have 2 theta equal to pi over 2, which would be pi over 4. Okay, so when I substitute in 0, I start off at 4. So I'm starting here. When I substitute in pi over 6, I'm going to have 4 times a half, okay, which is 2. So, but that's at pi over 6. So you're headed in this direction. And then when I take pi over 4, okay, which you know pi over 4 is here. When I substitute that in, I'm going to get 0. So when I just go from 0 to pi over 4, when I use those bounds of integration, that's going to be half of 1 petal. So it all depends on how they ask the question, okay? But you do need to have some clue how to graph these. All right, hope this video helped you, and we'll continue getting better at this when we do polar area. Thanks, kids.